Hi students. Okay, so this is our part 2 in chapter 4 in our PSYC 218 analysis of behavioral data, and we continue with measures of variability. So in the last part we talked about the range, we talked about deviation scores, we talked about variance derived from sum of squares, and we talked about standard deviation, which is the square root of the variance. And we talked about this with population data. So for the rest of this chapter, or the rest of this set of lecture slides and this video, we're going to look at standard deviation and variance for sample data. And this is important for a number of reasons. One, we hardly deal with small populations, or put it in another way, we hardly deal with entire populations. We often cannot find the population standard deviation or population variance. Oftentimes we're either given that information in the test, or it takes a long time to get that information because we're working with large groups of people. Again, in the thousands, hundreds of thousands, and millions, and so on. More likely, we are going to work with sample data, and we have to deal with something called sample bias or sampling error, because again, when we grab sample from populations, we're not getting everybody, and the best we can do with the sample is to get a sample that is representative of the population. That is through techniques like random sampling, where everyone in the population has an equal chance of being selected. And even then, with matters of probability, you are still going to get people that are closer to, either to the extreme or, closer to the mean. It really depends. And it's because, especially when you use random sampling, it is a matter of probability. We can't say for sure in one sense. So when we use sample data, the best we can do is get a sample that is representative of the population, and when we do have a representative sample, we can make inferences from the sample about the population. So which is why, again, you can think back to chapter 1 as we talk about the difference between descriptive statistics and inferential statistics. And inferential statistics always involves a sample data. Either by comparing a sample with a population, or inferring from the sample about the population, or comparing samples. And so when we work with the standard deviation and variance of sample data, we need to take special considerations. And here are some of these in point form. With sample data, we are going to go into the realm of inferential statistics, where we start to try and draw general conclusions about the population. Again, you can think back to examples like, oh, well, if, again, I'll use a really small population. Well, our population's 3 people, and these are their scores. If we only use 2 of them, and this can be any 2. I think that's kind of it, really, in terms of, let me double check. Yeah, 1 and 2, and 1 and 3. That's it in terms of the people I could grab. I could have different orders, but that's permutations, not combinations. I could do this, and maybe, oh, there's one more actually. Silly me. There, 2 and 3. There you go. And if I switch the orders, there will be 6 different outcomes. But anyway, if I grab any 2 of these, again, I'm not grabbing anybody. I'm not grabbing everybody. And so, because we're working with limited information, the best we can do is make inferences. And if the sample is representative, then we can make more accurate or more logical conclusions about the population. So we will be working with inferential statistics. And notice here, even with this small demonstration, our sample data is different from population data. So this is the key. Sample data differs, or differ, if we use data as plural, from population data. 1, looking at the spread here, you can see that in general, the samples would have less variability than the populations. Again, you can see that as well, even by the range. Again, you can also measure this in standard deviations, and you can see the population standard deviation here for sigma squared is not going, and then we'll go into standard deviation. Here we'll use S, okay, for sample standard deviation and sample variance. It's going to be less. We're going to have less variability. And so, when we compute or calculate the variance and standard deviation for sample data, we need to take into account that our estimate of the population data, or the value that we're going to get for variance and standard deviation, would be biased if we don't take into account sample size and the fact that, you know, we're working with sample and therefore limited information. And this is what we mean. Here is a more concrete example here with a more realistic data set. And let's look at this example. So here we notice our population variability is this wide, and this is our population distribution, which is, it looks, you know, normally distributed with one mode and is symmetrical. And let's say we grab a sample here. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people of I don't know how many, but the sample size is indeed 10. Again, let's assume that this sample has been randomly selected from the population, and it's, you know, representative as best it could, allowed for by the sampling technique, random selection. The variability here, taken at face value at these values, again, we know some things. One, the sample data are from people from the population. They're just selected to be the sample. They're not going to be anywhere outside of the distribution. You're not going to get any values out here. Impossible. Or these ones that are outside of the population distribution. That is not going to work. They'll always be within the population distribution. And also, they are probably going to have less variability than the population itself. This is simply because you're not going to grab everybody. You're not, unless you grab the maximum and the minimum at the same time. But think of the probability for that. Again, if indeed the selection process is random. So more likely than not, you're going to get a variability from a sample that is going to be less spread out than the population itself. So we must take this into account. In this case, in simple terms for this course and this chapter, we're going to do that by using something called degrees of freedom. That is sample size minus 1. And this here at the end here is little n, or lowercase n, not big or capital N. And why do we do this? Well, one, the sum of squares is calculated with the data we're using, so we don't need to change that. And the average in the sum of squares is just, you know, sample size. We don't need to change that. We need to keep this value accurate. We don't need n minus 1 in the sum of squares. However, when we try to calculate variance, that is the average squared deviation scores, we must acknowledge that our sample size is smaller than our population size. Which, in a way, if you think about it, the n-1 seems counterintuitive. Oh, well, we're going to make the sample size even smaller? No. There are two ways of looking at this. One is the degrees of freedom, where once we have made a calculation with our sample data, one piece of information is no longer dependent. And I can show you that in this degrees of freedom section. And another way of looking at this in a simple perspective is that when you divide something by a smaller number, the variance would be larger, or at least the result would be larger than if you were to divide by a larger number. Now, how come it's 1? Well, we'll talk about that with degrees of freedom. But in terms of using a smaller denominator, well, we're trying to correct the bias by making our variance of the sample larger than it would be if it was just n, because if we use n, well, that n is only reserved for the population when we have everybody. And so because we don't have everybody, we must account for this and we must correct the bias, and the way we do it is with degrees of freedom, which is n minus 1. And so instead of saying sum of squares is divided by, population size, which is sigma squared, our sample variance then is sum of squares with the sample data, including the sample mean, divided by your degrees of freedom. In this case, is sample size minus 1. And the standard deviation then is the square root of that. So if we use sum of squares, then we say it's the standard deviation of the sample is sum of squares divided by n minus 1. Here is lowercase n, and square root all that. So here's a first look at it first. Here's an example of a sample distribution, and a way we can tell here is look at the distribution and see what mean is used. If we see mu, that's population, the Greek letter mu. If we see the capital letter N, that's going to be, I'll use an arrow here, population mean, and then here is going to be sample mean. So that right away would tell us, even without looking at anything else, and the distribution would include this, or your question you want to find that out, see whether we're talking about the sample or population. And so because we're working with sample data, then we know the size is sample size. And so when we work the data out, and you can with this one, then we need to calculate the sum of squares. And then once we do that, we're not using sigma squared, we're using s squared. And that sum of squares, remember, we need to account for sample bias or sampling bias, and that's so n minus 1. And then our standard deviation would be the square root of this, or in this case, the square root of sum of squares divided by 1, or sum of squares divided by 1 and square root of all that. Again, you can work that out with this as well. And this is a head start. Again, you can work this. 11, it's going to skip a number. 7, 6, 5, 4, 3. And so we already calculated the mean, and I use m here, or x bar, but we'll use m for now. And we use the sum of squares. So we can do this. 11 minus 6.5, and minus 6.5, and so on all the way down, and then squaring these values, and then you'd get down here a sum of squares, and then with which you'll use n minus 1 to get your sample data, sample variance, and then you square root the sample variance to get sample standard deviation. If it sounds like you're saying a mouthful or thinking a mouthful, well, that's part of statistics too. Because we're working with specific values and we have specific names for them, it is very important to know and say and write those names properly. That's one of the first lessons I learned. So again, population data is population data. So you have to say, if you're dealing with population data, population standard deviation, for example. If you're using sample data, you're going to work with sample, sum of squares, sample, variance, sample, standard deviation. By doing this, you're going to avoid confusing yourself when you work with either set of data. And you're not going to mix up your formulas and techniques, so to speak. And so you can work these out. And this is a summary table which is calculated using a software. Again, you could find these on the internet. There are calculators for these, and you can just input the values. But again, I strongly recommend that you try and get these values. again, I hesitated with this one because I know, and I've done this, the standard deviation and variance is going to be some decimal point. So I didn't do it for this one. Again, when I do the demonstrations, I try to keep the data simple. And even then I made mistakes, as a teaching moment from the previous video where I divided 2 over 3 and got 1.5, where the answer is 2/3, which is 0.6 repeating. So again, always good to do your work and double check it to avoid such mistakes as well. And also doing the work would help you solidify your understanding of the concept and practice of the skills. Remember, before I say anything else, when you do sample variance, it's n, you divide sum of squares by n minus 1. And sample standard deviation is going to be the square root of, in brackets, sum of squares divided by n minus 1. Okay? And so the next bit is that degrees of freedom that I mentioned earlier. That is another way of saying n minus 1. And so what that means is, to put this in more plain English, it is the number of pieces of independent information. That's where you're going to get the word freedom from. And the degrees is sort of the number of pieces of information that is independent and free to change. And I'm going to show you this again with my simple data. Again, my simple population of 1, 2, and 3. Again, you can calculate the population mean, and again, I'm using population right now, and it's going to be 2. Yeah. And so, I'm just mentally double checking here. And so, with this, you can, for example, once you know how you calculate the mean, in this case it's, sigma x over n. Once you've added all the scores, okay, and you divided it by the number, so 1 plus 2 plus 3, and then you go, okay, n, this is 3, so it's 6 over 3, which is 2. Okay, and so notice here, if I knew that the mean, and the mean is calculated in a specific way with a specific formula, and there's only one way to do it, and the mean is 2, and let's say for some odd reason I lost one piece of population data, and so I only have 2 left, and we know, okay, I know there's 3 scores, and I know the mean of the score is 2, and I know one of the scores is 1 and the other one is 3. And so you can, using math, and go, okay, well, I know what that missing score must be. It must be 2. It cannot be 1. It cannot be 3. It cannot be any other number. It can't even be -2. It must be 2. For this whole mean to work, I must use 2. 1 plus 2 plus 3 is 6, divided by 3, the number of scores, which is 6 divided by 3, which is 2. So apply this in a sample sense, and I'm just going to change this to M here. And this is 2, not Z. N. And so when we work with sample data, again, now we're going to change our assumption here. And, instead of a small population, now we have a small sample. If we calculated the sample mean, one of these values, and only one, and I'll prove this to you very simply. Okay, let's say I erased 2 scores. So now you can ask the same question. What are the values of these missing scores? Well, you might think, oh, okay, well, I know it was 2 and 3 before. But if you have 2 missing values, and these values could be anything, then, it doesn't have to be 2 and 3 anymore. It could be 1 and 4, for example. It'll still get you 6, right? and divide that by free scores, and these are free scores, you'll still get 2, right? I could even just do, oh, isn't the second one isn't 1, the second one is 4. I could do that. It could be a decimal if I wanted to. I could make this 1.5 and then this be 3.5. It'll still be 6 when I add up all the scores. Sigma x is still 6. And then there's still 3 scores, so then it's still 6 over 3, and the mean is still 2. So then, if I, had 2 missing scores, then, I can't tell what the mean is anymore. So this is what degrees of freedom is about. When the outline says degrees of freedom is defined as the number of scores in the sample that is independent and free to vary, that means, except for one value that could be quote-unquote missing, and you know what it is if you know all the other values, for example, in this case, 2, degrees of freedom would say that this value here, which I'm going to shade now, is that piece of information that's no longer independent. That is, it must be something if you knew what the other values are, all the other ones. Which also then, to complete the definition, these other guys which I circled could be anything, as long as you know what they are. And then this piece right here, which I'm going to box again and shade again, that is the piece that is no longer independent, and that cannot change if you knew what the other values are, when you know how the statistic, in this case the mean, is calculated. And when you work with sample variance, you have done something. You have made a calculation. In this case, it's the average squared deviation scores, which you can go back and trace back and go, oh, if I'm missing a value, I know what that value is. So that piece of information is no longer independent. So that's the sort of story explanation to degrees of freedom. And this is the value we're going to use to account for sample bias. Because we know there's one piece of information that's no longer independent, we can't account that anymore. And so what we divide with to get our variance is no longer sample size n, but sample size n minus 1, which is degrees of freedom. And this has 2 effects. 1, we logically account for sampling bias. And 2, because we're dividing by a smaller number, our variance would be a larger estimate rather than a lower one, which would be closer as an estimate to population variance. Because remember, in our previous slide, by default, if we calculate sample variability by with sample size, it's smaller by default because we're grabbing a tighter distribution than the population distribution itself. Again, using random sampling. It must be the case. Again, the only way is by chance you happen to grab the largest and the smallest at the same time. There are only 2 ways to do it. One is by a very unlikely chance, especially for a large population, or you purposefully choose a large one and a small one. That is the largest and the smallest. Those are like the only 2 ways, really. Other than that, in likelihood, by probability, you're going to grab something that has a lower or smaller spread. And so we account for this with degrees of freedom, which accounts for sampling bias or sampling error. And this is going to be important as well as we talk about things like, error variance, or in this case, individual differences, especially with samples. But for now, before we get into that, let's review our population versus sample variance, specifically focusing on sample variance. So here we go. If a sample has 4 scores and that sample has a sum of squares of 24, what is the variance? Remember, here is sample, so your choices are 6, 7, 8, and 12. Take a moment and think about this. Read the question, and this is a good example here, a very good example of reading the question. And one of the ways this can throw you off is sample versus population. If you can't say in the question whether you're talking about a sample or a population, you're probably going to get it wrong, because if you're used to doing one sort of calculation, be it sample or population, and you don't read the question and it happens to be the wrong one, that is, you're using a sample calculation for a population question using population data, that's going to be wrong. Or if you do the vice versa, you do a population calculation for a question that talks about the sample, that's going to be wrong too. So this question, I've talked enough. You probably thought of the answer already or by now. So if you said 8, you would be right. And here's why briefly. Remember, we're doing n-1. So if you were doing sigma squared, you would use n, but we're not talking about population. We're talking about sample. So if we were to misread this as population, then the population size would be 4, and therefore sum of squares divided by 4, that's going to be 6. So that would be this one that you choose. But that's wrong, because we're not talking about the population. We're talking about the sample. So this will be wrong. Instead, we're talking about sample variance, which is n-1. Again, we talked about why we do this, to account for sampling bias. And then we'll see a comparison here too. Remember, this is a sample. The population is much larger than this. So this would not be an actual case either. So if you're thinking, oh, well, if I calculated variance for the population, for the sample data, and it looks smaller than the variance, well, that's because the sample size is small. And the population size is small, and the population is much larger than 4. So anyway, population here, and then sample here, and then it's 4 minus 1, which is 24 divided by 3, which is 8. So there you go. That's how we get that one. Okay. Okay. Next set of questions. A sample systematically has less variability than a population. True or false? And B, the standard deviation is the distance from the mean to the furthest point in the distribution curve. Those are sort of review questions, especially B. Take a moment and think about this. In question B, you might have to think a little further back. And if you answer true for A, you're right. Remember what we talked about. In random selection, where everybody in the population has an equal chance of becoming or being selected as a sample, by probability, you're probably going to grab a sample with a lower spread. You're going to probably grab more people from the average group. And think about this. Think about the distribution itself. Think about all the people that are, piling up in the middle, which means a greater probability of, being selected, because there's simply more of you. And each person has an equal chance of being selected. Again, extreme scores do increase variability, but they are less likely to be included in the sample because there are fewer of them, and therefore there's a lower probability with, random sampling for that person to be selected if they happen to have an extreme score. For B, no, that's not what the standard deviation is. The standard deviation is not to the furthest point in the distribution curve. It is, again, an standard or average deviation score, or I should say an expected deviation score. Again, remember, that's derived from your variance, which is your average squared deviation scores, or average sum of squares. Again, to put this another way, as the outline says, or as this answer says, it would be about halfway. Once you look at the data and you can compare from that to the most extreme score. It would not be all the way to the extreme score. That's more like the range, but that's not it either, because the range is the maximum minus the minimum. So again, review the definition of the standard deviation, which requires review of the definition for variance, be it sample or population, which also you need to review this definition of the sum of squares, which is absolutely essential for this chapter. So, more about variance and standard deviation. Remember, with the two measures, first being this measure of central tendency, we focus on the mean here, and the measure of variability, again, we focus on the standard deviation. They are extremely useful, or particularly useful, as it says here, for describing or clarifying graphs of distributions. Again, the graph by itself can say a lot, but once you put in reference points, like what's the expected value, the mean, and what's the expected variability, the standard deviation, then we can talk about the central tendency and the spread with actual numbers. Again, we must be careful about computing the sample mean and sample standard deviation. We use degrees of freedom to avoid sampling bias or sample bias. Technically, they're different terms. We'll use sample bias. Sampling bias would probably refer to the process of sampling. But that would be a Psych 217 thing here. Nevertheless, as the outline or the points say, means and standard deviations, when you do these correctly and when you interpret them correctly, again, just like the first point, would really help you describe the distributions that you see. Again, you can give numbers to the central tendency value, the expected value, as well as a number for the expected spread. When you show the mean and standard deviation in the graph, and before I talk about these points, and you can see some of these here. This is a histogram, and you can see, well, this shows the mean and the distances away from, well, the scores are away from the mean. Here's another one that doesn't show anything, and notice this slide doesn't show the mean or the standard deviation. You would, without that, you kind of go, okay, I would have to picture where the mean is, in this case being a symmetrical distribution with one mode. You go, oh yeah, I know the mean, median, mode is in the middle. That's cool. But again, there's no value for your spread, so there's really no way to tell. It could be any number. So, going back to this point, having actual numbers and showing this correctly on the graph for the mean and standard deviation is going to help you interpret the graph. So then here in the distribution, let's just use a bell curve for now, a symmetrical unimodal distribution. Having a vertical line in the center, the balance point, and show the location of the mean, or you just say what the mean is. For population, you use mu, or for sample, you use m, or, x bar for sample mean. That works too. A horizontal line to the left, right of both sides of the distribution. If you do one of these, something like this, and you can give a number, say 2, and the average here, it could be 0, let's just say. And you show that either with the line, and then you say, SD, sigma for population, or S for sample, then you'd show the expected spread or expected variability of the distribution by standard deviation. And one of these lines here will show one standard deviation above and below the mean. Again, using the mean as a reference point, which is why the mean is so important. Not just as a measure of central tendency, but also as the quote-unquote anchor, the point we use, the reference point we use for variability. In this case, variance and standard deviation derived from the sum of squares. So this is how we do it. This is the line we talk about, and again, you could measure it like this. But to put this simply, the simplest way to do it, and the most common way of doing it is, this is a line right perpendicular to the mean. In this case, again, it's a bell curve. It's a unimodal symmetrical distribution, and this is perpendicular. This one shows your standard deviation, which I'll label as ST, and this one shows you the mean right here, the vertical line. If you're not dealing with a curve or a frequency distribution polygon or curve, then you use an arrow to indicate the standard deviation. Again, this shows both directions, and again, assuming this is symmetrical, it would be both ways too. Right, and the mean again is that vertical line showing you where the expected value is as a measure of central tendency. So the last bit here, talking about sample variance, we're going to talk about it as a statistic, which we'll use for inferences. So the first bit here in our points is that the sample variance can be an unbiased estimate of a parameter when the average of the statistic is the same as the parameter. In this case, then you would happen to grab a sample that has a sample mean that is the same as the population mean. And it is possible to do this. And we want to do this, especially if we want to start making unbiased estimates of the population. Also, the average value, by default, uses all the possible samples from a particular sample size n. And these here is going to be something called, and it's going to be part of something called the central limit theorem, which we need to make a theoretical approximation of a theoretical distribution, a sampling distribution that approximates as closely as we can to the population distribution. So we continue. This is going to be like chapter 7 in our book. Okay. And then the sample variance then is calculated using the correct formula, which is what we already talked about, that we divide the sum of squares by n minus 1, which is degrees of freedom. On the other hand, the sample variance is going to be biased as an estimate when we use n. That is capital N, that is the population size, which one doesn't make sense, because if we use the sample sum of squares and we're dealing with sample data, why would you use the population size in the first place? And by virtue of the population size being much, much larger in real life, dividing a number by a large number with a large denominator, you are going to really underestimate the population the sample variance in this case. It's going to give you a really small number. So your sample variance would, if you use n, would give you something that looks like this because it's really small, because you're dividing by a large n. Whereas if you use n minus 1 using the sample size, and that number is going to be smaller, it's going to give you something like this. So you notice the spread is going to be much larger, and which will be a much more closer estimate of the population variance. Again, because the population includes more data, much more data, and so the size then would correspond to that and would give you the actual population variance. Again, we must account for this when we use sample data. We can't mix the population size with sample variance. We can't mix sample sum of squares with population size either. So then, going back, if we were to look at sample standard deviation in descriptive statistics, then when we use standard deviation in descriptive statistics, we are looking at standard deviation as a way to describe scores in terms of how far they are from the mean, the distance from the mean, the expected distance from the mean for each score. And we use two numbers really, the mean and the standard deviation. Again, these values here would say, okay, we're working with sample data. Again, it's not mu and sigma, it's m and s. Again, using these data would help us, more accurately show the scale of the central tendency and the variability on any given distribution. Again, this would be data like this, where we show the mean and the standard deviation, be it population or sample. The left one, distribution A, would be a population distribution. Distribution B would be a sample distribution. This noting the statistics and parameters used. A uses parameters, mu and sigma. B uses statistics, M and S. So just in case I forget to say it properly, I'm going to say it one more time. Parameters for A, because they're population, sigma and mu. Statistics is for B, sample, mean, and sample standard deviation. So here's an example of a sample distribution with its own sample mean and its own sample standard deviation. The sample size here is 20. The mean has been calculated as 36. Looks symmetrical for the most part. And the standard deviation has been calculated. Notice here, this is another block histogram. And these are actual values that you can use. And this is a sample. So again, you could, in looking at the values of this, you can actually calculate this. So if you were to start, you could go like this. Sample over M. And here is sum of squares. Okay, cool. Again, you'd get, okay, this, let's say this is 45, and then 43, and then 40, and so on. Each one of these, dot, dot, dot. And then you'd go, okay, 45 minus 4, no, not 4, 36. Okay, and then this would be 45 minus 36, like that. See? And then you do that for all of these, and then you can do a practice question and see if you get the mean of 36. Again, you'd add all these up to figure out what the mean is. And you'd know if you just do the deviation scores and add those up, you get 0 because the negatives would cancel out the positives. And then you can see if you can get a sample standard deviation of 4. And don't forget, for sample standard deviation, it's the sum of squares divided by degrees of freedom, which is n minus 1. So yeah, this is a good practice question to practice and see if you can get these values using the data here. This will help you practice several things in several chapters. One, you practice in chapter 2 in, population distribution table, and you practice chapter 3 getting the mean, and you'll practice chapter 4 getting the variability by calculating the sum of squares and getting the variance and standard deviation for this sample data. And you'll be practicing chapter 1 as well because you're distinguishing between sample and population. So these practice questions really cover all the chapters we covered so far. So make sure you give it a try. So again, if you don't happen to use a textbook or you don't feel like it or the textbook is overwhelming, there are already practice questions on these slides. Okay, here are some things that would happen when you start changing the scores in the distribution and what would happen to the mean and standard deviation. We've already talked about how sensitive the mean is once we start changing scores in the distribution, but the standard deviation, in a sense, is less sensitive. Now, here are some examples where the mean is quote-unquote more sensitive to changes in the score, where that means the mean would change if the scores do change, than the standard deviation, where if the scores change in the distribution, the standard deviation does not necessarily change in the following situations. If we add or subtract a constant to each score, again, here in this case we use add, and the constant could be positive or negative, then the mean would change by the value of that constant, again, positive or negative, but the standard deviation itself would not, because if you think about it, shifting a distribution, all of it, every score, does change the mean because the mean measures the center, or in this case, the expected value, because it's the mean. But the standard deviation doesn't change because you applied a constant to every score, be it positive or negative, so it doesn't change the shape of it. It changes the position, it shifts the distribution, but it doesn't change it. It doesn't I can't think of another S word that is like, shift. But it doesn't change it. It doesn't transform the distribution. This doesn't make it any quote unquote wider or narrower, which is a measure for standard deviation, which would be a variability measure. If you multiply the score by a constant though, and here is multiply, again, the constant could be an integer or a fraction. And it could be, a fraction that's less than 1, which would be division. But anyway, if you multiply a score by a constant, the mean is changed. Again, it would shift. But also because you're multiplying, then the standard deviation would be changed by the constant the same way that each score is multiplied. I'll put this in another way. The standard deviation would be multiplied by that constant. So not only would it shift, but it would also change shape. If you're multiplying by an integer, it would get fatter. It would get wider. So here's an example. If you got 1, 2, 3, and we shift the scores and multiply everything by 2, 2, 2, 4, 6. Notice, you can already see it right away. The mean's going to change. The mean here is going to be, I'm just going to use M here, 2. And here I'm going to use, the second mean here is going to be 4. All right, and so using sample data is going to make this a lot easier. We already know the sum of squares for this distribution is going to be 2, and then so here again, because we're working with sample data now, sigma is going to be 2 divided by 2, 1. Cool. Oh yeah, because it's 3 minus 1. No more mistake this time. That 3 minus 3 divided by 2 incident. Here, we got to do the sum of squares first. So let's take a look. I don't need F here. All right, so minus M, not mu. Okay, and then square that. Oh, okay, I'm running out of space. Let me try again. Okay, x minus m, and then x minus m all squared. Okay, I just need columns for this. Okay, 2, 4, 6. Nope, I need to write it properly. Highest value first. Okay, 6 minus 4, 4 minus 4. Okay, 2 minus 4. Okay, the arithmetic is fairly simple here, so I'm just going to do the squaring. That's 4. That's 0. And that's going to be negative 2 squared. That's 4 again. So our sum of squares here is 8. Cool. Okay, so for distribution 1, our standard deviation is going to be 1. Sample standard deviation, because I'm addressing these as sample data. Our standard deviation 2 here in this case, sum of squares 2, 1 here, and 2 here. Okay, and this is n1 and 2. I'm using subscript for different samples here. In this case then, I got 8. See, double check here one more time. Yeah, 6 minus 4 is 4. 2 minus 4 is negative 2. No, 6 minus 4 is 2. And 2 minus 4 is negative 2. Yeah, square that, and you're going to get 4 for both of these. 8 divided by 3 minus 1. I'll just write it here like that. Cool. 8 divided by 2, which is square root of 4, which is 2. Notice here, hey, look at that. I multiply all the scores by 2, and the standard deviation is also multiplied, 2. The standard deviation for the distribution that has every score divided by multiplied by 2 has the standard deviation being multiplied by 2 also. So again, this is just a short demonstration of how that works. Again, for division, it would be the same. So, if it was half, then it would be multiplied by 0.5. This would apply as well. So some things to keep in mind when you start changing the scale in terms of transformation, whether you shift it or, change its shape, as in wider or narrower. The mean is more sensitive that way. It will change no matter what. As soon as you start changing this distribution. But for standard deviation, it wouldn't change when you add a constant to each score. Again, the constant could be positive or negative, but once you multiply a constant, you would change the shape of the distribution, and therefore the standard deviation would also change depending on what constant you multiplied each score with. And the key here is each score. Okay, we're almost done here. In terms of inferential statistics, and we're looking ahead into the next few chapters here after chapters 5 and 6, where we standardize scores and look at probability. Variance and standard deviation is going to be the key to looking at inferential statistics. We need to figure out how far apart the sample data is, especially if we start to compare the sample from population, or more likely and more specifically, compare one sample to another. If the data shows a large spread for both samples, you would have one interpretation of whether the samples are different than if the samples have a lower spread. And we'll show that in the picture in a minute. But these points here would say that knowing the variance in our samples would help us figure out if the samples are going to be different. And this is the different part would be our meaningful and significant patterns. And most of the time we're looking for differences between samples and population, and more likely and more importantly and more specifically between samples. Okay, and so variability in this case then shows us how easily we can see these patterns. Again, if a sample or the samples, groups of data, would have a larger spread, that means there's going to be overlap between the samples, especially if the samples are graphed from the same population. And this variability then is labeled as sometimes as error variance, because we're talking about the spread of a distribution, be it population or sample, and the spread itself is individual differences. Some people score higher, some people score lower, most people score on the average. But yeah, because we are different and we score differently, some score higher, some score lower, not necessarily better or worse, but definitely higher or lower than average, then that would be considered error, because again, error here is the distance away from the mean. And this refers in this case to individual differences in terms of variability. And this is this slide shows us this in more concrete way using frequency distribution graphs. Here you see two distributions that have a relatively low spread, especially compared to experiment B or distribution B. Here you see there is no overlap between the distributions, between sample 1 and sample 2. There's absolutely no overlap. Yes, we can measure and compare the means. There is a clear difference between the means looking at these values. They are different. And then if we want to say whether these samples are different, and we're talking about the samples as a whole, whether the scores in sample 1 are really different from sample 2. And here, knowing that there's absolutely no overlap whatsoever, that is the highest score from sample 1, and here sample 1 being the distribution with the lower set of scores, and then compare that with sample 2 as the distribution with higher scores and the lowest score in sample 2, and neither of these overlap, then just by looking, we go, yeah, you know what? Because there's no overlap, and that's due to the variability being low enough that there is no overlap, yeah, we can say that these samples are different, not just by measuring the means as a central tendency, but we also factor in here the variability, the spread. There's no overlap because the spread is low, the variability is low. In contrast here, we look at a different experiment where the samples have a much higher variability. The spread is much larger to the extent that there is overlap. That is, even though the means are the same for the samples. Again, sample 1 has a mean of 35 in distribution A, or sample A, or experiment A, I should say. And sample 1 has a mean of 35 in experiment B as well. So notice here then, yeah, even though the mean's the same, 35 for sample 1 and 40 for sample 2, there is major overlap. that is looking at these in terms of blue and white, blue being sample 2, white being sample 1, there's lots of overlap. So if I would do a distribution like this, it might look something like this. Actually, because these have the same score, then it's just really like overlap like this, and like that. And I would just shade in the one with, I'll just shade in the overlap. And notice how much of the distributions, both of them have an overlap here. It would be like a Venn diagram like this. And you kind of go, wow, there's so much overlap between the distributions and between the circles. If we're looking at the Venn diagram, yeah, they're really close together. I can't really say anymore whether the two samples are really different because of the high variability. So keep this in mind. I won't say any more for the sake of this chapter, as this stuff covers, and we're going to talk about this in inferential statistics where we compare samples. But the variability is going to be absolutely essential as a factor when we want to compare samples. Again, whether that is comparing sample to a population to see if there's a difference between the sample from a population, to say, oh, whether that sample, really is different from the population, or compare between samples to see whether one sample is different from the other. So we end with a learning check, and then that's kind of it. So a long series of learning checks to review the stuff we've done so far. Question 3. Population, here, population, has a mean of 6, mu 6, and sigma, standard deviation for population, is 2. Each score is multiplied by 10. What is the shape of the resulting distribution? Again, you kind of have your choices. Take a moment to read these. I'll try to read them. I'm running out of saliva and my throat is getting sore. But anyway, mu is 60 and sigma is 2 for A. Mu is 6 and sigma is 20 for B. Mu is 60 and sigma is 20 for C. Mu is 6 and sigma is 5 for D. Think about what was discussed and what we talked about, and what happens when you multiply each score. What happens to the mean and the standard deviation? If you multiply both the mean and the standard deviation by the constant, in this case is 10, you'll be right. So again, the new mean would be 60 and the new standard deviation would be 20. Because each score is multiplied, both the mean and the standard deviation would change. Okay, last bit here. 2-part. So is this really question 6? I know what happened. That wasn't question 3. That was question 5. I'll change this real quick too. Question 5 and question 5. Okay, here we go. Anyway, question 6. 2-part, true false. Question A. A bias statistic has been influenced by researcher error. True or false? Keyword here is researcher error, which, you gotta figure out if it's the same as sample error. And B, on average, an unbiased sample statistic has the same value as a population parameter, or as the population parameter. True or false? Take a moment and review this in terms of sampling bias, or sample bias specifically. And what would make a sample statistic unbiased? And what does that mean in comparison to the population parameter? So, a bias statistic here is sample bias. Here, it actually refers to not researcher error, although it's possible. Here, it refers to specifically that there's a systematic effect that is, of using sample data. And we talked about this, that when we grab sample data from a population using random sampling, where everyone from the population has an equal chance of being selected, you're going to grab a sample that has a lower spread, a lower variability than the population variability itself. Therefore, that is the bias we're talking about. For B, once we factor in sample bias, and we produce a unbiased sample statistic using, if you thought degrees of freedom, little n, sample size minus 1, you're right. It would be a much closer approximation. It would have, on average, in general, the same value as a population parameter. And this is going to be key for chapter 7, the specifically central limit theorem. And I'll just finish by reading the point here, that each sample statistic differs from the population parameter. But if we average all the samples out, all of them, this would mean, doing this an infinite number of times. This is what we mean by all. But if we average all those out, that is the mean of the sample means, that would equal to the population parameter, because we do this infinite times and we do this for all the sample, and that means eventually we would grab everybody. And because we're using everyone's data, even though in a sort of quote-unquote roundabout way by using samples, and we would do this because, well, we can't grab everybody, we can only grab samples, and so the rest is theory. But we talk more about this in chapter 7, central limit theorem. This is going to be a very important part of our statistical procedures, in a very important story about that as well. But yes, it is true. An unbiased sample statistic, that is a sampling statistic, and if you don't know what that means right now, that's okay. We will cover that in chapter 7 as well. That would have the same value as a population parameter. And specifically here, it's going to be, we're going to refer to this as the sample, as the mean of the sample means, which is, the mean of the sampling distribution. But we'll talk more about that later. But yes, an unbiased sample statistic would have the same value as a population parameter. So that's it. In the last part here, we looked ahead to the other chapters, but in terms of learning outcomes, especially if you watched it this far, after over 2 hours, I presume, remember what we talked about in terms of the 6 learning outcomes. So we have described the purpose of measuring variability. We have defined the range of a frequency distribution and its limitations. We have computed the range, which is fairly easy to do, max minus min. We have described the variance and standard deviation, why we do it and how it's used. And we have calculated the sum of squares, variance, and standard deviation for a population. And we have done the same, again, sum of squares, variance, and standard deviation for a sample frequency distribution. And along with that, those would be our key learning outcomes. And again, you can look ahead to our other chapters as well, or at least keep that information, especially the bit about sample distribution, sample sum of squares, sample variance, and sample standard deviation as we finish off our chapter 4 and look ahead to our other chapters. Again, do those practice questions. You can use the actual data in our lecture slides as an example. Slide 36 with that sample distribution with some, integer answers for our mean and sum of squares and variance would be very useful as practice. You can also use the textbook. You can also use our web tutorials using Microsoft Edge or Apple Safari. And again, no substitute for doing the work and practicing. I'll keep reminding this so that more people would catch on. And if you got questions after these resources, that is the textbook, the practice questions, and even pausing and skipping parts of the slide and getting to the part you need, you can always email me directly in my email address, my college email address. This is an Alexander College course, so if you're learning this at Alexander College, you can email me at Alexander College, that Alexander College email address. So that's it. That was chapter 4. Next time we're going to do chapter 5, and until then, we'll see you in the next one.